Okay, so last time again, no, we talked about the different conformations of our alkanes and cycloalkanes. So what are conformations? Conformations are simply the rotations of the atoms within the sigma bond. No, wala ko model, but if you will have, for example, this molecule here of ethane, here, your carbon and carbon atoms, no? They are bonded to each other by what type of hybrid orbitals? Huh? Carbon here, this is your CH3, so that is your ethane. And carbon is bonded to 4 different atoms here. This one's bonded to 4 different atoms. 3 of the atoms are hydrogens, the other it's carbon, no? And also the other carbon is bonded to 3 other atoms. You have the hydrogen and the other one is carbon. And this carbon here utilizes what type of hybrid orbitals? Okay, nobody was able to study on that. So I'd like you to review because it will come out. Now that is supposedly have been discussed in Chem 16. So if you haven't recalled on Chem 16, I'd like you to review on the video that I shared. Okay, carbon here utilizes the sp3 hybrid orbitals. How does the sp3 hybrid orbitals came out? When carbon utilizes 3p orbitals and 1s orbital, sp3, diba? S1s, 3p orbitals, and it hybridizes. You know hybridization? It's like a mixture with the characters of the S and with the characters of the P. Okay, so that's a hybrid orbital. It utilizes sp3 hybrid orbitals. And carbon here utilizes 4 sp3 hybrid orbitals. So here, the one from carbon, hydrogen here. Carbon has 4 or utilizes 4 hybrid orbitals, forming a bond with hydrogen, forming a bond with hydrogen here, forming a bond with hydrogen, and forming a bond with carbon here. Hydrogen here utilizes only the s orbital. Hydrogen s orbital, hydrogen here s orbital. And carbon here utilizes 4 hybrid orbitals, sp3 hybrid orbitals to form a bond with carbon here using the sp3 hybrid orbital. So there is a sp3 orbital and sp3 orbital formation via the sigma bond here between 2 carbons. And there is an sp3 and s orbital bond formation between carbon and hydrogen, sp3s orbital formation between carbon and hydrogen, sp3 and s bond formation between carbon and hydrogen. Okay, there are 2 types of bonding. When 2 atoms form a bond by head-on overlap, which means that the 2 orbitals, if you have 2 atoms and they have orbitals, when they form a bond by the overlap of the 2 atoms, now in the molecular orbital theory, there is an orbital overlap. You know, if the orbital is made up of it's mostly space, it is the region of which the electrons most probably occupy. Okay, so when there is an overlap, head-on overlap, we call it an sigma bond. Okay? So this sigma bond utilized by carbon and carbon here by the sp3 orbitals, because in the sigma bond, it's possible that this bond between these 2 atoms can be rotated. Okay, so because of that rotation, our compound, organic compounds can take on several conformations. It's just like, you know, you can make a stand, you can sit, or you can pung different conformations by just the rotation. No? But it's not possible for for your legs, for example, that you can rotate so that ang imong front na sa likod, no, it's not possible. But for bonds, atoms, no, utilizing the bonds, possible that there is a rotation around its axis. And because of that rotation, there is what we call as conformation. Okay, so here is a form of conformation where there is a dihedral angle between this hydrogen atom and this to be 180. And between these two hydrogen atoms, the dihedral is 60. So you can make a rotation here, it's 60. And if you rotate that, it will resort to different conformation. Okay? So for ethane, for instance, no, if the two atoms, if you rotate that, and this hydrogen and hydrogen would have a zero dihedral angle, okay? This type of conformation is what we call as eclipse conformation. Okay, and if the other one, if the two hydrogens are far apart from each other as possible by 180 degrees Celsius, this is what we call as a staggered conformation. And among the two, which one is more stable conformation? The staggered or the eclipse? The staggered, this one, or the eclipse? Or the eclipse. It is the staggered because there will be less repulsion in this case, no, between our neighboring hydrogen atoms. And if you look at into the conformational analysis, the potential energy with respect to the rotation of the bond around the carbon-carbon bond, no, from the staggered, and we rotate this 60 degrees, and you will have an eclipse. There is actually a certain barrier that your molecule have to overcome in order to proceed to the eclipse state. No, and this is, you have 12 kilojoules per mole, and then if you rotate again by 60, it will retort back to your staggered conformation. And the most stable is the one with the lowest potential energy. Again, the reason is because there is less repulsion among the atoms. Okay, so there is also a phenomenon we also called hyperconjugation that favors the overlap between the unfilled sigma orbitals in the staggered conformation and the filled orbitals. And we call it hyperconjugation that helps to stabilize the staggered conformation. And the most important factor is the minimization of the steric repulsions in the staggered form. So what is this hyperconjugation? No, it happens, this will be discussed now when we go to chapter 6. And if you have a carbon atom, and then you have a vacant p orbital here, and here you have a carbon having an sp3 orbital here, okay, and there is an overlap between the orbital of the hydrogen here. They are adjacent to each other, you know, that the electrons here from the carbon hydrogen bond, sigma bond, no, will be able to share that electrons to the vacant p orbitals in the carbon. This is what we call as hyperconjugation. It will be able to help on the positive charge on the carbon. But we will discuss more of this when we proceed to chapter 6. No? But it also helps on the stabilization of our carbons. Okay, so the energy barrier between this staggered to the eclipse state is what we call as the torsional barrier. And so we can also expand that to a more complex, a longer carbon chain along a higher number of carbon atoms, now, such as butane. You can also expand that to a higher number of carbons, but you can have an anti-eclipse, a gauche conformation, and then you can have an eclipse again, and then you rotate that again. Now you notice the CH3 here. You have a gauche again, confirmation. This is also a staggered confirmation. And here another eclipse confirmation. So you will just have to look into your reference point. You will notice that you have to count that here, this is what we call again, the type of projection here. Is that itong tawag? A Newman projection. We are using this Newman projection to see. So how is, by the way, how is the Newman projection being used? Or how do we see the Newman projection? No? If you cannot, kanino, the Newman's projection, you can see that from this end. So you don't look at this, you can look at this molecule from this side, and this is what we call the side view, no? But you can also look at your molecule from this end, like a front view. So if you have to look at the molecule from this end, magtandi sila, no, na ito ang molecule sa likod. Okay? And have you tried the chem sketch? Okay, so you can play with that and you can rotate your molecule and you can actually stop it to make it in this, no? This is your front view from here, and you can actually draw that or make a schematic representation by the Newman projection. So you will have a triangle and then lignin and then circle rather, and then you have your hydrogen. And that means that the first triangle here, the 3 hydrogen is bonded to the first carbon, and the one sa circle, the 3 hydrogen is bonded to the end. Okay? And if, for example, carbon here is not bonded to hydrogen, but bonded to other carbon atoms like CH3, so you have your butane, you can replace this another carbon atom like CH3, so you can expand this Newman projection to higher number of carbon atoms. So you can have that with your butane. Mas maglibog ang uban, no? So with your butane, you have here, from the side, you can see it's like a zigzag with your zigzag formula. But you can also have your reference point. But you can see from this and this carbon lab. This becomes, for example, your, like your front. So your front, you have you have hydrogen, hydrogen, and CH3 like this, no? Hydrogen, hydrogen, CH3. And hydrogen, hydrogen, CH3. Hydrogen, hydrogen, CH3. So on the second, you can count 1, 2, 3, 4. On the second carbon, 1, 2, you have your carbon here, second carbon, you have your CH3, but it's second carbon, and then it's bonded to the carbon here, can circle, and then this carbon is bonded to CH3, this one. And so you can trace in that, and you can check the most stable one whenever you have the bulky groups. So you will have to identify which of the group of atoms is bonded or is more complex, bonded to your core in the Newman projection. So you have the bulky group CH3. When they are as far apart from each other as possible, the dihedral angle is 180 degrees Celsius. It is in the staggered conformation. And then you can rotate this 60 degrees, then you will have your eclipse. Rotate again by 60. Okay, you will have your CH3 here. You have a gauche conformation. Rotate again by 60. Then you have another eclipse conformation. Rotate again by 60. You have another gauche conformation, and rotate again by 60. You have your eclipse conformation. And if you can draw a conformational analysis of the butane, no, the stable one is the anti or the staggered, no, conformation, anti-1. No, and then you have to rotate. The potential energy of the molecule is increased by 16 kilojoules per mole, and you have your eclipse. You rotate again, you have this, you rotate again. When you have your CH3 and CH3 would have a dihedral angle of 0. There is so much repulsion with that because the group of molecules is large, and what will happen is that there will be a greater repulsion between CH3 and CH3. Okay? And you can compare that with this eclipse form here, where you have the repulsion between CH3 and hydrogen. But the repulsion is much greater when the CH3 and the CH3 are close to each other. Okay. So this is the most unstable eclipsed form of eclipse conformation of your betanes. Okay, you rotate again, you go back to gauche, rotate again, you go back to eclipsed, and then rotate again by 60, you go back to the anti. So which one is the most stable? You have the anti conformation. So you can think of the repulsive force of the bulky groups. No? So another is that the gauche conformers 3 and 5, which is 3 and 5 here. Kani, 3 and 5. How do we call the two? Is it the same or is it different? Okay, we call 3 and 5 as stereoisomers. They are examples of stereoisomers. What are stereoisomers? Stereoisomers have the same molecular formula, but same molecular formula, the same connectivity, different. The same connectivity, but different arrangement in space. Okay? So, particular, you have the conformational isomers 3 and 5. Na nag-differ sila, let's see. Nag-differ ang 3 and 5 here. Si CH3 is on this side. When you have 120 rotation, you have the CH3 on the right side. No? So they only differ in space and you call it conformational stereoisomers. The other type of stereoisomers is if the molecules have the same molecular formula but different connectivity of the atoms, what do you call? Constitutional isomers. So the conformational isomers are related only by bond rotation. Yeah, and we'd like you to read on the chemistry of the muscle action. Okay. Muscle proteins are essentials, are essentially very long linear molecules whose atoms are connected by single bonds like this. No? And relatively free rotation is possible about the atoms joined by single bonds. Whenever you see a single bond between carbon and carbon, carbon and hydrogen, carbon and other atoms, single bond only, it's possible for a rotation within the bond. And because of this rotation, when your muscles contract to do work, they are likely for the like they are for person showing exercising here. The cumulative effect of rotations about many single bonds is to move the tail of each myosin you have here, you know. So this is the muscles protein, the actin, and here you have a protein called actin, as I've said, no? And if you continuously move your muscles, no, what happened is that many single bonds is also able to move the tail of each myosin molecule here. Okay, and the process occurs over and over again as part of the mechanism. And because of that rotation. Now from alkanes, let's proceed to the cycloalkanes. No. The difference between alkanes and cycloalkanes is, of course, the first carbon and the last carbon. In the longest continuous carbon chain, they are connected to each other. And because of that, there is what we call actually as a ring strain. So, ng strain, it's a strain produced by the ring. That comprises, there are two types, the angle strain and the torsional strain. Okay, so what is the angle strain? The angle strain is the result of the deviation from the ideal bond size. If you remember, if you have your sp3 orbital carbon utilizing the sp3 hybrid orbitals, your carbon will have a shape of tetrahedral and the bond angle of 109.5. If the bond angle of carbon forming a bond with other atoms, no, is less than its optimum bond angle, then your molecule will experience angle strain. The other type of strain is the torsional strain. It's the result of the repulsive dispersion of forces that cannot be relieved due to restricted conformational mobility. Example, if you have your feet, no, and your legs in front, inyong feet is nasa front, right? And if you force your legs to rotate, palikod, can you rotate? Now, it's restricted, right? There is restriction. That kind of strain, if pugso ninyo, it's what we call as torsional strain due to restricted conformational ability. Okay, so let's study about the cyclopropane. Cyclopropane contains 3 carbons, and each carbon is bonded to 2 hydrogens and 2 other carbons. And you will look at into the carbon here, utilizes the hybrid orbitals, unsa? sp3. Okay, study on sp3, sp2, and sp hybrid orbitals. Review on that. It will come out again later. I'm gonna ask that in a quiz. So you have here your carbon utilizing an sp3, and it is expected that between carbon-carbon bond, it should have been 109.5. But because this molecule is a cyclic compound, carbon here is restricted to only have 60 degrees. So what happened? From the normal 105, na a variation ng 49.5 because it only assumes the 60-degree bond angle. And because of that, there is a great strain on your cyclopropane. If you look at into the 3D model here, you can look in a variety of way, okay? So you have on the side, you can also have a reference from this side, like this, no? And you have your sage that. You can also have the top view from this, okay? And you can expect here, you have the bond angle, bond length rather, 1.51 angstrom and 1.09 here. Because of the angle strain, your cyclopropane, because of the lower bond angle, your carbon here, 3 carbons here experience the angle strain. Normally, it should have the 109.5. So while the angle strain accounts for most of the strain in cyclopropane, it does not account for it all because the ring is not necessarily, because the ring is planar and the carbon CH bond of the ring are all eclipsed. You can see here, no? Even if you wanted, we know that the eclipse conformation would resort to strain, okay? So there is an additional strain. Even if you want that this hydrogen, pwede siya dili na lang side, right? But your carbon here is forced na dihalagid siya, carbon hydrogen. So the rotation is restricted. So aside from the angle strain, kani, napod siya torsional strain from repulsive dispersion forces. Okay, so it's actually less stable. So let's take a look at the cyclobutane. Your cyclobutane is made up of 4 carbons, okay? So you can think of different ways. Pwede nyo i-square. But kung i-square nyo mo si carbon, ito kayong bond angle, no? But actually, cyclobutane is not planar. You can have this kind of bond angle between your carbon here, carbon, carbon, carbon hydrogen here. The bond angle is 88 degrees. And normally, carbon should have again 109.5, but it departs from the normal. So carbon here assumes less than the normal bond angle. So cyclobutane would have the angle strain also. You can also, and the most stable conformation here is the folded or bent. It's not planar. You cannot expect your cyclobutane to be planar. It would tend to normalize because if it's planar, it will be very, very straight. So it would try to relieve that angle strain by assuming the optimal bond angle here. And this is the most stable conformation, the folded or the bent conformation, the cyclobutane. You can also see similar folded conformation with cyclobutane here, a cyclopentane here, 5-membered ring. You do not expect also your cyclopentane to be planar. You can expect here, so the other carbon is protruded above the plane of the pore, like here, no? If this is your 5-membered ring, you cannot expect na when you have your 5-membered ring planar, no? Why not na? So see triangle rod, there's cyclopropane rod and planar, but here you actually have a folded conformation here. And this one, how do we write on the you have here? Suppose this one protruded na siya nga end to relieve the angle strain. Again, if you look at into the bond angle, it will be less than the 109.5 here. So for a pentagon, for the internal angles of regular pentagon, it's 108. And it's very close to the normal 109.5. But if cyclopentane molecules were planar, they would have a very little angle strain. And planarity, however, would introduce considerable torsional strain. So therefore, by relieving that torsional strain, you have this. You see this one here? There's also like an eclipse if you look at here. So this one would try to relieve that torsional strain also, and it would end up having the non-planar formation of your cyclopentane. By slightly twisting to relieve that strain. So you do not expect your cyclopentane to be planar. It wants to relieve the strain brought by the torsional strain. Another one is the cyclohexane. So the cyclohexane is the cycloalkane that is the most stable conformation. So your cyclohexanes, there's so many ways of writing our cyclohexane. We have a regular hexagons, right? But if you look at the actual molecule of your cyclohexane rather, it's not actually planar, and it will assume the 109.5 degrees brought by the sp3 orbitals of your carbon here. So how would it assume and minimize the angle and the torsional strain? In fact, there is no angle or torsional strain in the cyclohexane. If you use the model, ChemDraw and ChemSketch, dili mo makita that it's planar. Actually, it will assume like a zigzag here. It's protruded. So the only planar is the 4 carbons, and the other carbon here will be protruded down, and the other will be protruded up. You call this one, so you see here. So this 4, 1, 2, 3, 4, it's planar. But above this plane, included above is just another carbon, included below is another carbon. We call, sorry. We call this one as the chair confirmation. Yan ang chairman siya. We know how to draw. So you just have to draw two parallels. Parallel one. Kaya na chair, let's see. So likuratan, sandiganan, and the end. You can also draw on island. Parallels. Okay. So likuratan, two parallels, and then sandiganan, and so here's and then fourth carbon is bonded to two other hydrogen atoms. Okay, so when you write on our cyclohexane, there will be what we call as the H-shell position of the hydrogens. Okay, later. So there will be the H-shell positions of your hydrogens. Okay, we have the H-shell and pictorial. So you have the H-shell down, you have H-shell up, so alternate H-shell down, H-shell up, down, and then you can have pictorial down, pictorial up, pictorial down, pictorial up, pictorial down. If you have this way, you have your H-shells up, sunod would be H-shell down, you have your H-shell up, H-shell down, H-shell up, H-shell up. And then pictorial down, pictorial up, pictorial down, pictorial up, pictorial down, pictorial. That's how you're right. When we rotate on the two carbons, on the bond between this one single carbon, when you rotate, all the other carbons also will rotate because otherwise it will bring torsional strain on the other. So it will follow to minimize the torsional strain. And in fact, if you try to move, from the chair, no, so you will have to relieve this pa-up. You have the half chair. So 1, 2, 3, 4 ka na hindi na. So mura siya gahigda imong diin. Okay, you have the half chair. But it actually brought, you see here that the potential energy for the chair conformation is very low. But if you try to move this, the potential energy increases for this conformation. This is very unstable. If you try to twist again for this, you have the twist both conformation. Okay, it is much lower than this. So the potential energy increases. And you have to move again this. Try na pag mo siya move. So pag relate mo ana or rotate siya dito. So you have the both conformation. This is more strained than this. So the potential energy increases. And then you rotate again. Balik ka sa twist both. Rotate again. You have the half chairs. The potential energy increases again. And you rotate again, you have the chair conformation. So the most stable one is the chair conformation. In fact, there is, here you can see that there is so much, what strain? So much, you have the torsional strain, you also have the angle strain. Because 1, 2, 3, 4, 5, it's almost like planar. So there is so much angle strain there. So the potential energy is very high. Here you twist a bit. You can see, if you will check that there will be torsional strain brought by katong eclipsing of the atoms. So the most stable here is the chair conformation. So how do we view that with the Newman projection? Okay, so you can have this different way of viewing. You have your hydrogens or other atoms now labeled as up, down, up, no, by the equatorial or the axial position. Again, your chair conformation of your cyclohexane would have none for the angle strain and none for the torsional strain. If you rotate again, so this is how we view by the Newman's projection. This, again, this kind of projection is what we call, pag makita na mag-circle, this is another way of showing our molecule for us to see the different conformation, like how much would be the dihedral angle between atoms. So this is a Newman's projection. You can see, you can have your carbon 1, carbon 2. Carbon 2 is attached to carbon 3 limit. This carbon 3 is attached to carbon 4, the bridge. Carbon 4 attached to carbon 5, the limit, and then carbon 6. Okay, so you have this. You will notice that all of the atoms here is in staggered or eclipse conformation. Staggered conformation. So there is no repulsion between atoms. And because each of the carbon utilizes the 109.5, therefore there is also no angle strain, no torsional strain, because here there is no repulsion. Okay? You rotate that again from here, no? Pag rotate, if you take this up, actually, puubos ni siya, na siya, wala kang model. Pag ana ni mo, pagsaka ni mo, kung down ni siya, you have your book. There is so much strain here. Why is, what type of strain? Torsional. Torsional, no? They are prevented, no, because of this. Too much torsion. And then you rotate again. So here the both conformation, actually you see that it is in the eclipsed form. The both conformation. And here is the twist conformation, mas more stable siya than the both conformation, no? Because there is less torsional strain here. Okay? Because of the greater stability of the chair, more than 99% of the molecules are estimated to be in the chair conformation. So you can also think of the higher alkanes like the cycloheptane, cycloheptane. And you will have to check, no, if what would be the, how much would the torsional strain and repulsive dispersion or the transannular strain, no, between atoms across rings. It's also possible, or the torsional strain. So you'll have to check. So conformations for higher alkanes, especially for N's greater than 18, no, you call this type of cycloalkanes to be catenanes. And these molecules are actually synthesized. However, if you have very large rings threaded on the chain, what will happen? That large rings are interlocked like links in the chain. So magsagol siya. And because of that, there is little space in the center of the cycloalkanes. Here. Cyclooctane. Mura siyang merge siya. Mura siyang maglibot siya within its ring. Diba ka ba naghulahop nga mura siyang libot-libot no nga. The number of carbon. So your carbon, we have so far had an example sa 6 carbons for cyclohexane. No, you can have cycloheptane, cyclooctane, cyclonine, but just know that you don't get a planar molecule because it may brought from, you have to find whatever or what is the bond angle between your carbon-carbon in the ring. Now, if it goes beyond or less than the normal bond angle, then it will bring angle straight. So again, let's go back to the most stable cycloalkane, which is the cyclohexanes. Just know that there's that H shell and equatorial hydrogen groups. Okay, so I'd like you to practice on how to write on the chair conformation, because in the real molecule and in the synthesis, during the synthesis, no, the H shell or the equatorial positions of the atoms will matter. So you have to know how to write, how to view in the chair conformation. So if you are in this, the right side, ang imuhang pataas is on the right side and paubos here is on the left side. I showed you how to write on our position, the H shell and the equatorial bonds on this carbon. If you flip this one, and you get still the chair conformation, what will happen is carbon 4, this is H shell equatorial. The pink is saan na H shell. So if you flip this, baliktaro nga ito nga kanin sa ubos mataas, sa taas ubos. Okay? Pag flip na to, and we still get the chair conformation, the H shell here will become the equatorial. Equatorial down, pero down yapon siya. We don't expect it. It's down here. When we flip, it will still be down here. This, but equatorial. Okay, pag-rotate na to amin. So we will rotate this, rotate, rotate, rotate. Every carbon-carbon-carbon bond will be rotated. So resort to the chair configurations. But here, again, the H shell here will become equatorial. The equatorial will become H shell. But carbon 4 will be up to the side. Carbon 1 will be down. What's the name? H shell equatorial. Equatorial will be down. So down siya, equatorial, it becomes down H shell. Up H shell becomes up equatorial. Okay, but still assumes the equatorial. Why would it be so? Because all of the rings, all of the bonds, single bonds, carbon single bonds will also be rotated. To go back again to the chair conformation. So if you have molecules here, you have your H shell becomes equatorial here. So what happens on 3, 2, 6 carbon? So the 5, okay, with 5, the pink is up, H shell, up, equatorial, right? Down, equatorial, down, H shell, up, equatorial, up. So you just have to do the alternate, okay? Okay, because if you miss when the bond rotates, no, you will have a different probably stereoisomer. So you have to follow, if you have to change and flip sa inanimate form. This is still chair, but the position of the H shell and equatorial atoms will now be different and it will matter. Okay, example. Methyl cyclohexane. So here you have your methyl cyclohexane. Found your chair confirmation. And then you flip this side, down ni siya. Pag flip na to, up na siya. This carbon here will be up. And this carbon here will be down. Okay? So remember, when this is down, because up by CH3, CH3 will be still up. But in the equatorial, no? You cannot, because your CH is restricted by the torsional strain. You cannot break the bond para ibutang mo siya otro sa axial, no? There is a barrier for that. It will lead you to a different type of isomers. You call it stereoisomers. The connectivity would still be the same and all others. So you have this confirmation, another confirmation, chair confirmation, but where do they differ? Huh? Where do they differ? Right. Asa man ay differ? So which one is more stable? The axial CH3 or the equatorial CH3? The axial equatorial. So CH3 manggod, it is in the axial. It's very close to all other atoms here. Hydrogen. Whereas if the CH3, it's oriented away. You notice, you view from here and this, so it is in the gauche. It is in the staggered conformation. The dihedral angle here would be like 60. If you have here from this and this, mura siya very close, it will bring strain because of the repulsion of these atoms here. Okay? So between this, if you have a bulky group, if you are to choose which conformation you always have to choose for your bulky group is equated in the axial or equatorial? Huh? Equatorial position. So here is another model of showing the methyl cyclohexane. The first one is the axial methyl, the other is the equatorial methyl. So you notice that this bulky group CH3 here is much less strained and far from the other hydrogen atoms. So studies indicated that the equatorial methyl actually brought stabilization by 7.6 kilojoules per mole. And because of this stabilization, between 1 and 2 conformation, when your methyl cyclohexane will be in its container, at which conformation will it assumes more? 1 or 2? Kung kamo ba, asa man mo mas komportable ka nang magsige mog higda whole day or ka nang magsige mog tindog or magsige mog lingkod? Most of the day. But most of the day, asa man? 8 hours? 4 hours may higda. Magbaktas-baktas, makasurvive ba mo kuan? Lakaw o 8 hours? Or 8 hours nga lingkod? Most of the time, kung i-count nyo ba, if you track your activity daily, asa may mas kuan, maglingkod, maghigda, or magtulog? Ha? Maglingkod kaysa maghigda. So that's for you. Now, if you consider this methyl cyclohexane, which do you think will most of the time this methyl cyclohexane assume, the conformation 1 or the conformation 2? Ano naman? Because it is more stable, less strained than the 1. So asa man mo mas dili ka po yun, maghigda, maglingkod, magtindog. It depends on you. Okay, and because of that, no, you have to choose on the conformation that will bring more stability to your molecules. In this case, the equatorial methyl conformation is more stable and 95%. So you will see the equilibrium position here. A big arrow is directed towards the equatorial methyl because most of the time, or 95% of the time, it will assume the equatorial position. Klaro ba? Okay, you can actually go with other types of cyclohexane, no? Actually, you can also do conformational analysis using the, ano sa'yo tawag ani? Using the Newman projection. Okay? Yes. Newman projection. So here is your Newman projection of your methyl cyclohexane down. So this is equatorial. And this is the Newman projection of methyl cyclohexane eggshell. Okay? So you will notice here that there is closer distance between this and the other. So there is greater repulsion between the other atoms as compared to say because staggered siya dito. You have a gold butane also, and also brings their string here like this. 3.3. So much higher actually repulsion that's not by the two gauge interaction. Where is that? This gauge interaction and this gauge interaction. So you will notice that the destabilizations would be about 7.6 times the aluminum. So you can also analyze if you have other than the methyl, you could also analyze with other alkyl groups attached to your cyclohexane. Okay, so it's the same. And you can also have if you have two substituents, it will actually give rise to the cis-trans isomers. What is a cis-trans isomers in cycloalkanes? The cis-trans is brought by the restriction of the bond rotation in your alkene. So you cannot rotate this because saan you rotate? You cannot have this. Right? Parotate pa ni ito, one pa ni siya, and you cannot have that. So the cis can only go to trans if there is a bond broken. Okay, so that's why there is a different type of isomer for cyclohexane brought by the cyclic ring. No, so you have the cis-trans isomers. This types of isomer is what we call as stereo isomers. But are they conformational isomer? Yes or no? Huh? No. No, they are not conformational isomers. Rather, they are stereo isomers. Here we can have your cyclohexane. Your cyclohexane here is, how do you call this? 1, 2, 3, 4. 1,4 dimethyl cyclohexane. Okay? If we flip this one, oh, by the way, is this cis or is this trans? Trans. If we flip this one, you still get your trans. Okay? But which of this first structure and the second, how do you call the two? Are they stereoisomers or conformational isomers? Huh? Conformational or stereo? Conformational or stereo? Conformational. Stereo siya kung cis and trans. Pero kung pareho siya trans, that's still pareha siya trans, but na-change siya through the rotation of the bonds. Okay? So which one is more stable, the first or the second? Why? The stage 3 is in the equatorial position. And why would the bulky group stage 3 more stable here when they are located in the equatorial position for cyclohexane? Huh? So there is minimization of the repulsions and so delegation strain with other neighboring hydrogen atoms. So here is the cis 1,4-cyclohexane. So the first and the second. Okay? The first, what's the name? Cis 1,4-cyclohexane. If we rotate this, what will happen? You get a cis gapon. So the 2 is called conformational isomers. Tama. But which one is more stable, the first or the second? Huh? Okay, in this case, huh? Same na siya, kay pareha man siya trans here, equatorial. Okay? So there are different ways of writing our cis and trans isomers in the cyclic alkanes. Cyclic or cycloalkanes. No, you can write by chair, especially the cyclohexanes. You can write by the chair, or you can also write by the top view. If you write by the chair, so you have to remember on the horizon ninyo, or the now ninyo. So if it's up, equatorial, it shall. It shall up, it shall down, it shall up, it shall down, it shall it shall up, it shall down. Down, out. No, it depends because you have the CH3 man. We cannot choose because you want to, this is a cis. So if you have the 1,4 cis, so 1, 2, 3, 4, this is up. 1, 2, 3, 4. Your CH3 should be up, kay cis man. So because of that, you have up, down. This becomes equatorial. Okay? Equatorial because you have the cis, and with this 2 it's equivalent, but there's 2 way of writing or different way of writing. You can use the top view for the cis and the trans isomers, so you can use the wedge. So the wedge, when it's dark, is oriented towards you or away from you. So mura kag nagtan-aw top view of the cyclohexane, right? So it's towards you and the other is away from you. So this type, this depiction is trans or cis? It's trans. So you have to know how to write that in trans, like that. Okay? And if you want the cis, you can write 2 ways. So you have 2 dash toward away from you or dark towards you. That's still dash. That's still cis. Consider each of the following conformational structures and tell whether each is cis or trans. Letter A, cis. Hi. So many. Letter A is cis or trans? Cis. Letter B. Huh? Letter B is letter C. Okay na. Answer. Sakto mo? So you have cis, and okay. So when two confirmations of cis, so I consider another one, no? This one is cis or trans? Cis. If you flip, cis yapon. Which one is more stable, the first or the second? Anong first man? You also have the equatorial here. Okay. So you choose the bulky group, the more bulky group that is in equatorial position. So even if you have an equatorial position here, but the bulky group, the third butyl is in the axial, while here it's in the equatorial. So which one did we choose? We can predict that this one is actually the more stable because there is less repulsion brought by these bulky groups to the other atoms. If you have this in the axial, there is a greater repulsion with the other neighboring atoms. And because of that, there is more stabilization brought by the equatorial position of the third butyl group. So most of the time, the conformer is the first or the second. It will be the first structure that this third butyl for methyl cyclohexane will assume, the first structures. So in general, if you have one ring substituent group is larger than the other and they cannot be both equatorial, choose the larger group that is in the equatorial. Okay? So I think that's all, and we will have our problem sets given in the online. Do you have questions?